Question 7. A ball of mass 3 kilograms traveling at 4 meters per second hits a wall and rebounds at 3 meters per second. Calculate the loss of kinetic energy of the ball. So kinetic energy calculated as half mv squared. So if we're being careful here, what we should probably do is draw a diagram. So before we've got something of mass 3 kilograms traveling this way at 4.0 meters per second. Afterwards, we've got something that still has a mass of 3.0 kilograms traveling this way at 3.0 meters per second. When we're doing the calculation for the change in kinetic energy, we need to be a little bit careful because of the squared term, but it's also true that if we treat the 4 as positive and 3 as negative, the squared term means the negative part disappears anyway. Kinetic energy is a scalar, not a vector, is I suppose the other thing we could say. So all that matters is the magnitude of the velocity. So the kinetic energy should be equal to half times the object's mass, so that's 3.0, and then multiplied by the difference between its initial velocity squared and its final velocity squared. So 4 squared minus 3 squared is obviously 16 minus 9. It's not equal to 1. So this is a sort of common mistake that people make at this point. So we've got 0.5 times 3 times 16 minus 9. So 16 minus 9 is 7. So the value here should be 10.5 joules. The change in momentum of the ball. Now here we need to be more careful because momentum is a vector. Whenever we're dealing with vectors, it's helpful to draw vector diagrams. This thing has an initial momentum mv in this direction, which we could work out the size of is 3 times 4, so that's 12 Newton seconds. It has a final momentum of 3 times 3, which is 9. I'm going to draw it separately to start off with, approximately the right scale. Its final momentum is 9 Newton seconds. Now, the mistake that you don't want to make is to think we're going to combine these two vectors tip to tail, because these two are not being added together. We're going to take the initial velocity of the ball, the initial momentum of the ball, and add the change in momentum of the ball to find the final momentum of the ball. So these two vectors should be arranged tail to tail. When we draw them, this means that now we can draw in our change vector, which is the one that runs all the way along the top. The change, and on my diagram, I can immediately see that it must have a value of 12 plus 9, which is 21 Newton seconds. So I've drawn the initial in blue, added the change in orange to find the final in green. So change is equal to 21 Newton seconds. Both momentum and energy have a law of conservation. Explain why the situation above does not violate these laws. So for energy, their kinetic energy has reduced, but it's going to be transferred into other forms. We'd expect thermal, sound, but probably mostly thermal. As the ball hits the wall heats up, the ball heats up as it rebounds. And in terms of momentum, there's been a large change in momentum. We could phrase this one of two ways. I think what we'd probably say is that this is not an isolated system, that we did not consider the momentum of the wall, perhaps we'd say the earth with which the ball collided. So the ball is observed changing momentum because we've not measured the momentum of the thing that applied a force on the ball when the two collided.